Okay, so we are going to look at some problems here, and I'm actually just going to do a couple example problems from the text here, um, and we'll talk about our sinusoidal analysis here. So I'm just grabbing a calculator here so I have something to do computations as we're going about here. So this is actually going to be just problem 9-30 from the text. So let me just go ahead and draw our circuit here. Plus minus, resistor, inductor. This is 2.5 millihenries. .5 microfarads here. This is 20 ohms. This is 10 ohms. This is 5 ohms. And we're looking for I out here. And the problem tells us that Vs is equal to 25 sine of 4000 t. Alright, so trying to find that current I out. Now, one thing that some of you might think of doing right now, if we're trying to find a current, just let's do some loops. I'm actually not going to do it that way, and the only reason I'm not going to do it that way is that I'd have to write 3 loops. Not that this other method is going to necessarily be a lot shorter, but it is going to, I think, help us with this. Now, before we do any kind of equations or anything like that, we know we need to first put this in phasor notation. So, first thing is to recognize that my voltage source is a sine function, so I need to translate that to a cosine function. So it'd be 4000 t minus 90 degrees, which we know just goes to 25 at an angle of minus 90 degrees, which in rectangular form is minus j 25. And of course I forgot maybe to write here, this is just in volts. Okay, so that's my Vs, and I'll go ahead and write this here as minus j 25. Alright, because I'm going to erase some of this so that we can keep the circuit here as we start writing equations here. But the next thing we need to do, of course, is we need the impedance of each of these components. And so for the inductor, my impedance is, of course, equal to j omega L, which in this problem, this would be j, omega is 4000, and then L is 2.5 millihenries. And then I'll do that real quickly on my calculator here. 4000 times 2.5 millihenries, and this is equal to J10. And again, this would be in ohms. So let's go ahead and put that right here, J10 ohms. Alright, then what do we have? Well, I need the impedance of the capacitor. So the impedance of the capacitor would be minus j over omega c, which is equal to minus j divided by 4000 times 12.5 microfarads, which I'll move this up just the tiniest bit here, and then I'm going to move it back down. And so we'd have 4000 times 12.5 microfarads, and then we're looking at the inverse of that, and this is equal to negative j 20 ohms. Okay, so I will go ahead and put that in our circuit diagram here. So minus j 20 ohms. Alright, now we have everything as far as we're ready to be able to start doing some circuit analysis. So what I'm going to do here, as I said, is I'm going to first erase some of this stuff so that we can write some loop equations So if you haven't copied it all down, just pause the video, of course, back before I'm erasing to copy everything down. Alright, so I'm going to do nodal analysis, and the reason I'm going to do nodal analysis is that if I look at this node right here, and I call this VA, and I look at this node VB, I can clearly see, and I'll put it off to the side here, that I out is simply going to be VA minus negative J 25 divided by 5 ohms. I'm sorry, I have it backwards there. So let me erase that and actually write it correctly, because remember, it's what's at the tail of the arrow minus the other, so it would actually be minus J 25 minus VA over 5. So that's what I out would be. So that's why I'm going to try and find voltage A and voltage B. Alright, so what do we need to do here? Well, actually I want to keep it there so I can see the circuit diagram. Well, we're going to just do our simple node analysis, and of course, you know, when we do this, if I look at node A, I'm looking at the currents going out here. So let's write our equation down here. So this would be VA minus negative J25 over 5 plus VA, and of course it'd be minus 0, so I'm not going to write that, over J10 plus VA minus VB over 10 equals 0. Now, just like we've done before, we're going to multiply through this equation to make things a little bit easier here. So I would probably multiply through by, well, in this case, I'm actually only going to multiply through by a 10. And I'll show you, I mean, you could do J10, that's fine. But I'm only going to multiply through by 10 here, because I'll show you something we can do here when you have J's in the denominators. So if I multiply through by 10, we would have 2 VA, and then I have a negative negative, so that would be plus J50 plus VA over J plus VA minus VB equals 0. Now you might say, oh, well wait, you've got that J in the denominator. Well, let me show you something. If you just multiply this by numerator by J and denominator by J, you'd have J times J, which is J squared, and J squared is just negative 1. So what we wind up with is, instead of plus VA over J, we wind up with minus JVA. And so if you have a J in the denominator, you can always move it to the numerator, and all that happens is you flip your sign. And that's because if you multiply numerator and denominator by J, you get a J squared in your denominator, which gives you a negative 1. Alright, so now let's combine terms. Well, first off, I'm going to move this term to the other side and then combine things. So I've got 2VA plus VA, and I've got minus J. So I'd have here 3 minus J times VA, and then I have minus VB is equal to minus J50. Alright, now again, if you don't have all of this copied down yet, I would pause the video to make sure to copy it down, because I'm going to start writing another one. I'm going to first write this off to the side here, just so I have it here. So I'm going to write 3 minus J VA minus VB equals negative J50. So I'm going to kind of put this off to the side here, just so I can keep track of that, because I'll need that in a second. So now I'm going to erase this again so we can look at the circuit. And once we have this, I won't need to erase anymore. I'll just move down on the page here. But again, you can always pause to write some more things down. So now we're going to look at node B here. And of course, this is again just standard node equations. So what would we have here? We'd have VB minus VA over 20 plus VB, I'm sorry, I was getting ahead of myself. This wouldn't be VB minus VA over 20, it would be VB right here minus VA divided by this 10. Alright, so VB minus VA over 10 plus VB minus 0 over 20, and then plus VB over negative J 20. Now I'm going to do, and this is all equal to 0, I'm going to do the same thing I did before, which is instead of multiplying through by the J, I'm just going to multiply through by the 20. And so then we would get 2VB minus 2VA plus VB, and then I want to move that J so it's not in the denominator, so it just puts it in the numerator and makes it positive, plus J VB equals 0. Now we're going to group terms again together, so what do I have here? I've got minus 2 VA plus, then I'd have 2 VB plus VB, so that's 3 VB plus J, 3 plus J times VB equals 0. Alright, so I've got my two equations. I'm going to move up here now, move this down here. So I'm going to write these two equations that I've got here. So I've got my first equation that I got was 3 minus J VA minus VB is equal to minus J 50. Great. My other equation I have is minus 2 VA plus 3 plus J VB equals 0. Now the question is, how do we solve this system of equations? Now you could do kind of a, oh, this top equation is easy to solve for VB. You could solve for VB, substitute in, and then you get a single equation with VA, and that'd be fine to solve. And it actually wouldn't be too difficult to do, but I'm going to do this a different way here. And what I'm going to do here is show us how to do this using matrices. Now if you have a TI Inspire or like a TI 89, your calculator can actually just do matrices with complex numbers. For some reason they didn't add that functionality to the 84, which quite frankly I think is kind of stupid, but they didn't. But there's a way around it. And we talked about this at the end of last semester, so you know, this may or may not be familiar, but we did talk about it. So let's talk about how we do this. Well, we're going to make a giant matrix here, and basically what we're going to have here is we're going to have a matrix, and what we're going to do is we're going to do real part and then imaginary part. So I'm going to have, for VA, I'm going to have 3, and then I'm not going to put the J here, I'm just going to put what the imaginary part is, minus 1. Then underneath it, you do the conjugate, so it'd be plus 1, and then 3. Okay, now that's our term for VA in the first equation. So that's just done this piece right here. Now if we look at this one here, you don't have to write this out, but what is VB? This would be negative 1 plus 0 times J times VB. So what does that mean as far as my matrice? Well, this would be minus 1, 0, 0, minus 1. Because the conjugate of 0 is still 0. Okay, then what about the minus J50? Well, I'll put it off over here to the side. You could think of minus J50 as 0 minus J50. And so what would be inside the matrix? I would have 0 minus 50, positive 50 because I do the conjugate, and then 0. So this is setting up just my first equation. Now we're going to do the exact same thing for the second equation. So I'm going to have minus 2, 0, 0, minus 2. 3, positive 1, negative 1, and then 3. And then 0, well that's easy. I'm just going to have 0, 0, 0, 0. So that's my matrix. Now we plug that into our calculator and do reduced row echelon form. So if we do that, and we do the reduced row echelon form, what we end up getting here is the following matrix. We wind up with 1, 0, 0, 0, 6.25, negative 18.75. And then 0, 1, 0, 0, 18.75, 6.25. And then we get 0, 0, 1, 0, 0, negative 12.5, 0, 0, 0, 1, 12.5, and then 0. Okay, so what that means here, and I'm going to star this here for us, what that means is we now have that VA is equal to 6.25 minus J 18.75 volts. And then we have that VB is equal to 0 minus J 12.5 volts, which of course is just minus J 12.5. Alright, so of course we've got our voltages now, and we could convert those back into, the polar form or whatever we want to do here, but what we need to do now is to simply find out what I out is. Now remember that my I out is going to be minus J 25 minus 6.25 minus J 18.75 all divided by 5. And so if we do that, we would wind up with negative 6.25, and let me see here, 25 minus J 6.25 all over 5. And so what we would wind up with is that I out would be 1.25 negative minus J 1.25. Now what we want to do is of course convert that back into my polar form here. So I'm just going to do this real quickly on my calculator here. So I type in that answer, and then I do math, complex to polar, and we get that I out is equal to, we'll round it to 2 decimal spots, 1.77 at an angle of negative 135 degrees. So then if I want to write I out, it's going to be 1.77 cosine of 4000 t minus 135 degrees, and then making sure we keep our units correct here, I was doing voltage divided by resistance, not kilo ohms or anything, so that means that would be amps. And so that's all we're going to do in this video. Next video will be another example problem talking about doing Thevenin equivalence.